Well, first of all, good morning to all those participating in this virtual presentation, and it's always a privilege to take part in these, and I certainly appreciate the opportunity to do so this morning. As far as by way of introduction, I've been in the industry for quite a few years. I started out working for combustion engineering. My background is primarily in metallurgy, and have worked a good deal in high temperature applications of power plant materials. And so the presentation today is going to be directly related to that. I do want to call attention to the fact that the topic has changed a little bit from what was originally announced. And the reason for that is that the original presentation that I had intended to give was really focused primarily on metallurgical related issues. And I thought it might be good for a couple of different reasons to broaden the focus a little bit to encompass a topic that would be more directly related to the operation of the combined cycle plants, dealing not in this particular case with the HRSGs, but with the high energy piping associated with the plants. And so what we're going to be looking at today is some of the issues associated with the high energy piping in these plants, and particularly the main steam and hot reheat piping, and look at some of the issues associated with the metallurgical issues, but as those metallurgical issues bear on things like welding and the welds themselves and repairs associated with those welds, and then with the inspection of the welds. I do want to make mention of the fact that most of the information that's going to be presented here is not particularly new. A lot of this information has been, or a lot of the data and things that we're going to be discussing have been known and been around for a number of years, at least 20 years. The reason for going through this again is that I think as we all recognize, there have been some profound changes within the power industry, and a lot of the constants and certainties which we took for granted for so many years no longer exist. And I mean, as an example of that, you have only to look at the status of the legacy OEMs, the companies like Combustion Engineering, Foster Wheeler, B&W, and looking at where they are now compared to where they were 30 years ago gives you an idea of just how much the industry has changed. And with that, a lot of the people that have come into the industry over the last 15 to 20 years have not had the opportunity to participate in the information sharing, which is at one time was such an essential part of the integral operation of our industry. And so that really is I guess the justification for reviewing this information. Although it is said there's nothing new for a lot of you, it very likely will be new based on the experiences we've had in talking with people at the various plants. And just to emphasize that point, I want to just relate one very brief anecdote that hopefully will make that point. About a year ago, there was a tender that was put out, which was dealing with a utility who wanted to have an inspection done on their high energy piping, and so they put out a request for quotation and got several different responses to that. And the way the request was put out was that the utility wanted each of the potential providers to define exactly what would be their inspection program. And one of the responses the utility got was, and by the way, this was for grade 91 piping. The piping system involved, piping was entirely fabricated from grade 91 material. And so one of the responses they got was to conduct a survey of the length of the piping to detect any damage due to FAC, or flow assisted corrosion. Now, those of you who may be familiar with the issues here would know, of course, that that's not something you would look for in grade 91 piping. And when this was discussed with the plant people, they were not aware of this. Once it was discussed, they thanked us for educating them. But at the end of the day, the upshot was that company that had suggested that particular inspection got the contract because they were the low bidder. And so I think that speaks to where we are in the industry as a whole and why reviewing some of this information can be so important. So with that, let's get into the presentation. What we're going to be talking about fairly briefly is we want to look at metallurgy, and particularly the metallurgy of welds, particularly as it applies to where they're operating at elevated temperatures, and so where creep damage is involved. As part of that, we'll look at the basic structure of welds and how that may influence how damage occurs and where damage will occur. Talk briefly about NDE, the issues there being how to characterize any indications that may be found in welds, looking at things like the size, the orientation of the indications, trying to identify the nature of the indications, because that can be very critical in determining what steps should be taken when an indication is found. And then looking briefly at some of the issues associated with weld repairs, so that when damage is found at a weld, what are the appropriate steps to take in order to return that weld and that component to full serviceability. As far as the objective of the discussion, if you can achieve a basic understanding of how damage develops in welded components that are operating at high temperatures, then from the standpoint of the NDE specialists, that give them a better idea of where to look for damage when they are doing an inspection, how to look for the damage, what are the appropriate techniques, and then when damage is found or when indications are found, how to interpret those indications to determine whether what they're seeing is something that's critical to the operation of the component or something that may have been there since day one and is relatively benign. And then from the standpoint of the welding engineers, if they understand how the damage develops, they'll be in a much better position to develop a program to implement the appropriate repair. What we're going to be talking about is generally defined under the rubric of high energy piping. That's the intent here is to apply this to piping systems in industrial type plants that operate where these components operate within the time dependent regime. Now, for those of you who are not familiar with that terminology, the time dependent regime, from a code standpoint, there are two general design regimes that are identified, one of which is called the time independent regime, and that's where the components are operating at temperatures where creep is not an issue. So in the time independent regime, it is understood that unless some specific damage mechanism intervenes, there is no functional design life for the component. The component would, in the absence of any kind of extraneous damage, would basically operate forever. Now, opposed to that, of course, is the time-dependent regime. That's what we're going to be talking about today. And these are components that, because of the temperatures they're operating at and the stresses that they're operating at, it's understood by the designer that they will have a finite life, that at some point in the future, they will fail, regardless of an external damage mechanism, and that the mechanism of failure will almost certainly involve creep. These systems are a particular problem for engineers that are responsible for the reliable operation of the plants because creep is a progressive damage mechanism. And by the nature of the design, in most cases, when the damage does occur, it will involve creep in some capacity, although there may be other damage mechanisms that are contributing to the degradation. So in the high energy piping and power plants, and for the combined cycle plants as well, you're generally talking with the main steam and the hot reheat steam piping systems. The intent, of course, is to transport steam from the steam generator to the turbine, the steam turbine, and they typically operate in the temperatures somewhere between the range of 950 to 1100 degrees Fahrenheit, and from 550 to 5000 psi pressure. Now, talk very briefly about creep. Again, those of you who may not have had to deal with creep in any systematic sense, this is going to be a very brief overview, but at least give you a general idea of what we're talking about. And so if you take a material that is not operating in the creep regime, and you load that material or apply a stress that's below the yield stress of the material, there'll be a certain amount of strain that will accompany the application of that stress. And if you hold the stress at that particular level, that strain will be maintained at that same level for regardless of how long you apply the stress. So there'll be no, unless you increase the stress, there will be no increase in the strain. Creep, however, is a different matter because it is the time-dependent strain that accumulates at a particular temperature and at a stress that's below the yield point of the material, or that can be below the yield point of the material at that temperature. And so oftentimes when people are describing creep damage and the strain accumulation associated with creep damage, you'll see schematic curves such as this, which identify a primary, a secondary, and a tertiary phase of the creep damage. This is a highly idealized picture of creep strain is developed. The important thing here is that as creep damage is accumulated, as reflected in accumulating creep strain, that over a period of time, that the rate of that damage will accelerate as more damage is accumulated, and ultimately will end up in failure.
Jeff, sorry if I could interrupt for a second.
Sure.
Back on that slide.
Sure.
Just in case some folks don't know, maybe you could briefly define the difference between stress and strain.
Sure. I guess in the simplest terms, stress is the load that is applied to a component. In the case of a section of piping, for example, that's transporting steam, that stress is going to be the hoop stress or the internal stress from pressure. Strain is the movement or the change in dimensions of the material in response to the stress. So strain is a physical deformation of the material. The stress is the load that's applied that causes that deformation. If that helps. Bob, is that adequate?
Yeah, that's perfect. Thank you.
Oh, okay. Now, in terms of creep damage, we said that creep is time-dependent damage that will gradually and accelerate as assuming that a constant stress is maintained. And depending upon the temperature and depending upon the level of stress that's applied, creep damage can manifest itself in a number of different ways. But for the temperatures and stresses at which these piping systems generally operate, what you will typically see with creep damage is just as is evidenced here.
Good morning, TEC. This is Derek Roberts.
In any case, the damage that develops is a diffusion control damage. It has to do
Who's this?
with
Who is this? We've talked before, Anna, I believe.
I think we've got some interference. Okay. In any case, at the temperatures and stresses at which these piping systems typically operate, when creep damage manifests itself, it often will manifest itself in the form initially of cavities, which are actually holes that will form in the material as a result of accumulation through diffusion of dislocations in the crystal structure that pile up normally along grain boundaries triple points at grain boundaries. And when they
Can you hear me? Okay, thank you. I'm not sure. My headset
Sorry about
went into
that.
mute mode, and I had to just cycle the microphone up and down, and it reset. So what's going on?
uh,
Can you hear us, the fellow with the headset?
Yeah, I took care of it. Sorry about that.
Okay, no problem.
Okay, no problem. All right, so in any case, early stages of the damage will show up as these small microscopic holes in the material. And with progression of the damage, you'll see more of these cavities that will develop. Ultimately, they'll begin to link up to form microfissures. And with additional accumulation of damage, you'll get macro-cracking and failure of the component. So the challenge here, as you can imagine, the particular micrograph that you're looking at, the original magnification was roughly 500 times magnification. And so the challenge for any kind of inspection is to find this kind of damage as early as possible. This is a good indication of the evolution of the damage. You can see in the on the micrograph on the left, this is basically non-aligned cavities. The middle micrograph is aligned cavities. And then on the right would be microcracks and macrocracking, which would represent an advanced stage of the damage. What I'd like to draw attention to, though, is that those of you who have dealt with suppliers who will come in and evaluate damage, oftentimes you'll see descriptions of the damage that will go through a progression from isolated cavities to oriented cavities to microcracks and to macrocracking. And that description of the damage is applicable for certain structures, particularly for coarser grain structures. It's not necessarily applicable to fine grain structures. And as we're going to talk about a little bit shortly, when we look at the where the damage can occur, there are different microstructures associated with those different locations. And so the damage can manifest itself in different ways, depending upon where in the welded structure the damage is actually occurring. And so, for example, in so-called type 4 regions, many of you will have heard the term type 4. That generally refers to the region on the outside edge of the visible heat affected zone in a weld, where you tend to have very fine grain size. In those cases, you won't go through that same progression of damage of isolated to oriented to microcracking, macrocracking. Instead, you'll go to individual random cavities within the structure. There'll be a higher and higher density of those cavities as damage progresses, and ultimately the material will simply tear apart. So be aware of that distinction. One thing to keep in mind too, in terms of defining the life of these piping systems, for those systems that have been designed in accordance with the ASME boiler and pressure vessel code, for example, the components should operate reliably for at least 250,000 hours, depending on the material type. But this assumes, first of all, that the piping system support of the piping system is properly maintained, that the steam generator operates within design limits, and the material from which the piping system is fabricated is properly produced, and the components are fabricated and installed properly. In terms of end of life, if you're dealing just with regular base materials, so the sections of the piping between two girth welds, for example, if you were to encounter a situation in which that piping would reach its end of life, the visible manifestation of that would be quite obvious, in that under normal circumstances, these materials have very good rupture ductility, and so the evidence of distress is going to be seen as swelling of the piping. And if the damage progresses to the point of failure, what you'll see is, as is shown in this picture, almost like a fish mouth type failure in the part once it's swelled to a very significant extent, oftentimes in excess of 10 to 12% rupture strain. Now, where the problem has come in is when most of the failures that occur in these piping systems occur at welds. And in the, of course, in the high energy piping, that means that the damage that occurs, the wells open, does involve creep, which means in turn that we have to consider the complex structure of the weldments in trying to determine what will dictate the life of the component. A very well-known example here in the United States anyway, and this is going back to the mid-1980s, there were two highly publicized failures that occur in long seam welded components. These were in traditional coal-fired power plants on hot reheat line, piping. In both cases, these failures occurred at the weld seams. There was no gross swelling of the piping involved. In fact, there was virtually no indication of any distress in the piping prior to the failures occurring. And in both cases, these failures occurred at a fraction of what would have been the expected life based on consideration of the properties of the base metal. Now, there was as you would expect, there was a lot of work that was done following these failures to try to understand why they did occur, and a lot of the information that came out of that has been critical in defining the inspection programs that are typically applied to these high energy piping systems in order to effectively try to monitor the accumulation of damage over time. All of these systems contain welds. So I drew attention to these failures in the long seam welds, and thankfully we've learned enough that there are not many long seam welded components in the combined cycle plants. I'm aware of only a few clamshell welded elbows and things like that. But they do. These same issues occur in other welds in the piping systems, most notably in the girth seam welds. But then you have pipe-to-pipe saddle welds, lug attachment welds, radiograph plug welds, all of which can be locations of problems as the piping systems age. In discussing, as we will here shortly, where damage occurs, it's important to understand that, and I think many of you probably do understand this, but for those of you who do not have much background in welding, welds are very complex structures from a metallurgical perspective. When you make a fusion weld, you're obviously adding metal that is up at the melting point of the alloys involved. This means that the material immediately adjacent to the weld deposit will have seen temperatures very near to the melting point of that material, and then there'll be a gradient of temperatures radiating outward from the weld deposit that have seen very high temperatures, but decreasing temperatures as you go away from the weld itself. That has certain implications for the materials we're talking about, has certain implications for the microstructures of those materials, because at each particular temperature increment, there will be a change to the microstructure associated with that temperature increment. And with the change in the microstructure, that also means there'll be a change in the mechanical properties associated with the material at that local area of the weldment. And so many of you will have heard terms like the weld deposit and the heat affected zone. And a lot of cases, when those are discussed, it's all the implication is that the heat affected zone is a nice homogeneous structure, and in fact, it's not. It's a very complex structure. There are multiple substructures that develop within the heat affected zone, and each of those substructures has its own unique set of properties that will define how it responds to temperature and stress when it's put into service. So with that, if we now take a typical weld, and this would be in a thick walled component, and typically when weld of this type would be made using the submerged arc welding process, simply because it's the most economical process in these cases. And if we look at a weld and look at the various parts of the structure of that weld, what we can see is, and what we have learned over the years, is that there are multiple areas in which, depending upon the unique or the particular set of operating circumstances and the particular materials that are being used in the particular circumstance, that there can be multiple areas where damage is likely to creep damage or creep dominated damage is likely to occur more rapidly than in other areas. And why this is important again is because when we're doing inspections on these systems, it's important to know where to look and it's important to know where to look to so that you have the best opportunity of finding damage if in fact it exists. So when looking at these, the kind of areas that we know from experience can be vulnerable to premature or to accelerated damage due to operating conditions are, first of all, the weld metal immediately adjoining the fusion boundary. Another area that very commonly, and this relates to the type 4 region, is the fine grain intercritical region of the heat affected zone out at the edge, number 2. Number 3 would be in the heat affected zone structure, but more closely located toward the fusion boundary. So in what oftentimes would be called the coarse grain region of the heat affected zone. Area 4, this is basically a subset of the type 4 region, but it's actually in the weld deposit itself. And it's in situations where you have the kind of stacked weld bead configuration that you can see in this particular weldment, where you created a continuous heat affected zone structure or fine grain heat affected zone structure within the weld deposit itself. Number 5 is showing an area along the weld bead center line. This is not as common, but there have been instances where damage has occurred here. And then number 6 is at the fusion boundary itself. This just gives a brief rundown of what it is that in the structure that leads these particular areas to be vulnerable to damage. I'm not going to spend a lot of time on that right now. But I want to give some examples of the damage that has been found in welds operating in piping systems at each of these locations. So first one was at the weld metal adjacent to the fusion boundary. A couple of things to note here. You can see that this is creep-related damage that has developed immediately adjacent to the fusion boundary in the weld metal. You'll also notice that there's no heat affected zone here. So this weld has been normalized and tempered. And the vulnerability here is related to the 2 things. First of all, the accumulation, the preferential accumulation of inclusions related to the welding process that was used that make this area more vulnerable. And the second and very important factor here is the significant difference in the creep strength or mismatch in creep strength between the weld metal and the base metal. And it's this creep strength mismatch along with the geometry at this point that has resulted in the damage actually initiating subsurface down in what's called the cusp region of the weld. Again, that's a very important consideration. If you're doing an inspection, you have to understand where the damage may actually initiate so that you can apply the appropriate inspection techniques. The examples I'm going to give here are all taken from long seam welds, but these same areas of vulnerability exist whether it's a long seam or a girth seam or another type of weld. This is actually a girth seam weld showing failure along the same location in the weld metal immediately adjacent to the fusion boundary. In this case, the weld was given a subcritical heat treatment, so there is a heat affected zone, and yet despite the presence of the type 4 region, that damage has actually occurred in the weld metal because in this particular case, in this particular set of circumstances, this was the more vulnerable area, and so that's where the damage actually formed. This was a situation in which section of grade 91 piping was welded to a valve body using grade 22 filler metal, and as a result of that material combination, immediately in the region immediately adjacent to the fusion boundary in the weld metal, the material was preferentially decarburized. The carbon actually diffused out from the 2 1/4 material to the grade 91 material, the 9 chrome material, and left a region in the weld metal adjoining the fusion boundary that was uniquely susceptible to damage because it had basically been decarburized. Now, there's some other issues with this that we'll talk about later, but important thing here is the location. I'm going to go through this a little quick. This is the typical type 4 damage at the outer edge of the heat affected zone. There have been many examples of failures related to this type of damage. The damage in the heat affected zone structure adjoining the fusion boundary. Examples here. See, there are several different reasons that you can have damage in this area, one of which is the potential for reheat cracking in the coarse grain heat affected zone, which has very high creep strength, but very limited rupture ductility. And then there's the classic example of the damage in the heat affected zone immediately adjacent to the fusion boundary in the dissimilar metal welds. Excuse me, the old dissimilar metal welds that used to be made with austenitic stainless steel filler metal. In those cases, the damage was preferential in the heat affected zone due to decarburization that occurred and due to the mismatch in the coefficient of thermal expansion. Show you examples of damage in this stack bead configuration running across the artificial heat effect, continuous heat affected zone created in the weld deposit itself. Show you there have been some examples where, due to the particular chemistries of the filler metals used at the center line of the beads, actually was more vulnerable to cracking than other locations. And this is examples of cracking here. And then in dissimilar metal welds, and particularly we've seen it most recently with dissimilar metal welds involving grade 91, where we have damage at the fusion boundary itself. And this is creep-induced damage that is, develops at the fusion boundary, usually associated with carbides that are formed in the filler metal that's used, nickel-based filler metals. There have been occasions where environmentally driven cracking has formed right along the fusion boundary in the base metal, in the grade 91 base metal. And then this is an example of damage in a dissimilar metal weld, grade 91 to type 316 piping, where nickel-based filler metal was used. And you can see here the creep damage forming right along the fusion boundary. So all of that is to say that when the message I hope comes out of this, the weldments are, when you look at it from a metallurgical standpoint, are incredibly complex structures, that there are multiple areas in those structures where, when the material is being operated at elevated temperatures, can serve as preferred zones of weakness. And in any given set of circumstances, that the zone where the damage may go more rapidly, and so would be the area of primary concern in any type of inspection, can shift from one location to another. And that's what I'm getting at with this. It's a horse race, because in any given situation, any one of these locations could be a preferred location for the damage. Now, in terms of the inspection, I think, as most of you are aware, there are a number of tools out there that are commonly used for the inspection of the steam line piping. One of these is ultrasonic testing, and any of the various versions of ultrasonic testing that are available now for these inspections. What you're trying to do, as with any use of any of the non-destructive inspection techniques, is to find the damage as early as possible, and then when you do find indications, to accurately characterize those indications. It's important to understand that when you're looking at these welds, simply the fact you find an indication doesn't mean that indication represents advanced creep damage. It could be, for example, an initial flaw in the weld that was introduced during the welding operation itself. And if there's been no growth from that flaw, then that's an important piece of information that would be used in determining what the next step would be once the indication is detected. And so to find the damage, first of all, you have to use the proper tools. If you're in a situation where there's potential that the damage could start subsurface, then the surface inspection techniques like dye penetrant testing or magnetic particle testing or metallographic replication are going to be a very limited very limited value, because they typically won't find the damage until it's very far advanced. And so in those cases, it's going to be essential to use one of the volumetric techniques like ultrasonics or like radiography. Give you a few examples of some of the complications that may arise when you're doing these inspections. These are mostly taken from long seam welds only because there have been so many inspections of long seams. But again, these same issues would hold for other welds also. So this was a case where inspection did find indication near the root of the weld. In this case, you look at the damage, they were looking at it with sensitive ultrasonic techniques. They did recognize that there were signatures associated with the indication that, to the individual that was running the test, suggested to him that there might be some growth associated with that. As a result of that, they did take a core specimen, and we found that not only that the original call in regard to the flaw was correct. The flaw was an initial weld flaw, but there had been growth, damage growth associated with that, which the NDE technician was able to identify from the signature that he was receiving in his equipment. But when we looked more carefully at that, we also found that there was fairly reasonably advanced creep damage associated with the weld that the NDE had not picked up. This is another example of an indication that was found near the root of a weld. Again, it was an original welding defect. As was shown earlier, there was damage that was propagating from the ends of this defect, which was what prompted a taking of a sample for destructive analysis. And then when we looked more closely at other areas, we found that there was fairly advanced damage in other locations, again, that the NDE had not picked up. And again, another example of indications that were found in the weld. And then when they were looked, it was confirmed that this was creep damage, but there was damage at other locations that was not detected by the ultrasonics that was being used, simply because it was below the threshold of detectability for that technique. Many of you will see, I'm going to try to wrap this up reasonably quickly here because I'm running out of time, but many of you have seen these, that looking at the different inspection tools that are available and what their abilities and what their limitations are. Replication, of course, is a surface technique. It will find damage at a very early stage if you're looking in the right location, but it is, for the most part, confined to the surface. Destructive sampling, of course, will find damage at its very earliest detectable stage, as well as macro damage, and then looking down at the various other techniques, what they can and they can't do. Many of you will have seen these kind of schematic diagrams showing that for the different, if you're looking at UT in particular, where along the progression of creep damage, each of the different techniques are effective in finding damage, which obviously relates to their overall sensitivity. And the issue here is, again, you're trying to find the damage at the earliest possible stage, because that's what's going to give the plant the greatest amount of lead time in order to take corrective action, whatever that action might be. The time of flight diffraction method has a particular level of damage that it can detect. Go to linear phased array. It also has a particular level of damage that, based on that particular technique, it's able to identify. And then what's called focused annular phased array, or there are other techniques now, these matrix type techniques that are able to focus the sound energy in a way that can give a higher level of resolution to what can be seen by the technique. And so these would represent really probably the best level of resolution that can be achieved with ultrasonics. And so in those cases, you can find the damage at a slightly earlier stage. Okay, with that, we've described the types of damage that can occur, where the damage can occur. We've looked at some methods of trying to find the damage using either surface or volumetric techniques. Now, in situations where you have found damage, you've determined the damage is service-induced. The next step that needs to be considered anyway is how do you execute an effective repair in that particular case. And so the things that should be kept in mind, first of all, you need to understand the root cause of the failure. It's very difficult to carry out an effective repair in a particular area if you don't know what caused the failure. And the reason for that is, particularly where creep damage is involved, if you don't understand the root cause of the failure, it's very likely that you will not be accurate in determining how much of the material needs to be excavated in order to accomplish the repair. Another thing that should be kept in mind is that even though you may be looking at high temperature components, not all the damage in high temperature components is necessarily creep dominated. It can be fatigue dominated, for example, and that has certain implications in terms of the repair that would be carried out. And then related to what I was talking about in the first instance, the NDE may not detect all the damage that's developed at a weld. And in those cases, and when there's any question at all, then it really is essential to do destructive examination so that there's a good understanding of exactly how extensive the damage is. Because if you leave damaged material in, it's very likely that there'll be rapid recracking in the areas that were not removed, and so that the repair in that case will not be as successful as it should have been. So some of the issues that you want to do, understand the root cause, factor in things like plant operation. An obvious situation here, does the plant cycle heavily? Are there situations where the plant has operated at temperatures above design? That would be an important consideration in trying to understand why the damage is developed. System stresses. Is the piping system properly supported? Have there been problems with the support system that would raise concerns about particular areas along the system where stresses above those anticipated might have developed? And this is just drawing attention to that. Other requirements: consider the original design and the fabrication. I had shown the failure earlier in which, because of the very poor design, there was a premature failure that occurred in a dissimilar metal weld between grade 91 piping and a valve body. If you don't have a good transition, a good smooth transition between components, that can lead to enhanced stress concentration and early creep damage, all of which will come into play in determining how the repair should be carried out. The importance of sampling can't be overemphasized, in particularly where creep is involved in the damage. Then it oftentimes is essential that samples be taken so that there is a good, firm understanding of exactly where how extensive the damage is, so that the repair can be prepared accordingly. And in some cases, it may be possible to use replication, depending upon the particular circumstances associated with the damage. But in most cases, taking a sample out, since you're going to be doing a repair anyway, is the most effective and cost-effective way of handling it. Then the other thing is that although there are occasions where you might want to consider temporary repairs, recognize that given the economics of running a plant, that oftentimes temporary repairs tend to become permanent. And there are implications associated with that in terms of both the reliability and the safety of the operation that must be taken into account. A couple of other considerations: it's always best to carry out repairs in a controlled manner. If you can avoid doing the repair immediately, if you don't have a good understanding of exactly what the root cause of the damage is, and if by doing a fitness for service study, you can demonstrate that you can operate with some level of damage in a component, then in those cases, the most appropriate thing to do is to defer the repair until there's a better understanding of what the cause of the repair is, and then when the appropriate time comes, carry out the repair in the most effective manner. The failure mechanism is going to drive the repair method. I think from what we've discussed, that should be apparent. When creep damage is involved, oftentimes, particularly if the damage is associated with some portion of the heat affected zone, then part of the excavation or part of the success of the repair is going to be ensuring that all of the damaged material is fully excavated, which means extending the excavation beyond the limits of the heat affected zone of the original weld. And then finally, be cognizant of material characteristics, depending upon what type of material you're dealing with. There are a few austenitic stainless steel systems out there, so things like stress corrosion cracking or sigma phase embrittlement could be considerations that would be taken account of in any kind of repair, because failure to do that would result in a failed repair. High strength steels, things like hydrogen delayed cracking, or the enhanced susceptibility to hydrogen delayed cracking should be taken into account. There may be ductility issues that need to be accounted for. And then, of course, with the creep strength-enhanced ferritic steels like grade 91, all of the thermal processing and the control of the thermal processing has got to be at a much higher level of control than even for other materials. And the maintenance of the microstructure during any kind of weld repair that's carried out must be maintained. So with that, I apologize. I've probably run over a little bit. Apologize for that. But if there are any questions, I'll be happy to try to answer them.
Yep, we've got a few. In the interest of time, I'm going to just read the questions rather than take the time to have people unmute and so forth. And I think we might be able to get through them. So the first question, Jeff, is primary and secondary creep detectable, or does detection normally begin at the tertiary stage?
That's a great question. And for what we're talking about normally, under normal circumstances, what we're looking at is damage that's occurred in the tertiary stage of the creep life of the component. It's very unlikely that the primary stage of creep is really just during the first few hundred hours of operation. So you wouldn't be looking for damage there in any case. And a lot of the materials we typically deal with don't even have what's a true secondary. They go directly from primary to tertiary anyway. So the answer to the question is you're generally looking at damage that's occurred during the tertiary stage of the creep cycle.
Okay. Real quick question is the cracked reheater pipe that you showed early on, was that seam welded or seamless in that example?
I think all of the pipe I was showing was seam welded.
Okay. On the failures at Monroe and Mojave, thought to be type 4 failures, or did they initiate in another region of the weld or heat affected zone?
No, that's a great question. And the failures at Mojave and Monroe were not type 4 failures. They were, both of those welds had been normalized and tempered, so there were no heat affected zone present. And the failures in those cases, the damage was concentrated in the weld metal adjacent to the fusion boundary.
Okay. You've used the term elevated temperatures a few times. One of the questions is, could you give quantitatively what are elevated temperatures?
Probably the easiest way to, and again, that's a very good question. Probably the easiest way to define that, most practical way, is if you go into the ASME code section 2 part D and look at the allowable stress values. The allowable stress values are differentiated based on whether they're controlled by creep or whether they're controlled by the tensile or yield strength by italics. And so the allowable stress values that are controlled by creep are given in italics in section 2 part D. As an example, for grade 22, for example, the italicized values start at a temperature of around 950 degrees Fahrenheit. So that would be considered in the time-dependent regime for grade 22. For grade 91, it's up closer to 1050. And for each alloy, it will vary slightly depending upon the the elevated temperature strength of the alloy. But from a practical standpoint, if you're trying to understand where creep is likely to be a significant factor in the life of the component, that's a good place to start.
Okay, thanks. All right, this one's a little longer, but I'll read through it. When preparing a pipework inspection program for NDE and replication, and there is a need to rank the wells, do you advocate the use of a pipework flexibility program such as Caesar, or do you need to use a finite element program where the actual operation of the pipework supports can be represented? Or if neither of those, what do you recommend to determine which wells are critical?
Well, certainly for the systems we're talking about, the main steam and hot read line piping where creep is an issue, then going through the inelastic analysis is certainly the best way to proceed, because that will take account of any movement of the piping system and any change in the support of the system as a result of creep effects over time. So, I mean, it's not that an elastic analysis isn't useful. It can be useful in pointing you in some general directions, but to really get the best picture of the condition of the system, I think the creep effects have to be taken into account, and that can only be done with the inelastic analysis.
Okay. You mentioned boat samples are critical for determining root cause if a repair is required. As opposed to manually obtaining a boat sample, are there any automated machines and techniques available?
There is equipment that will actually cut a boat sample out, where you've got a cup-shaped saw blade that will make that. The other thing, of course, is that you can take a plug sample out. So it's just like there are arbors that will give you plug samples anywhere from 1 inch in diameter up to about 3 to 4 inches in diameter, in which you can basically get the full width of the weld within a plug sample, and that will give you the kind of comprehensive information that is oftentimes needed in order to identify exactly how extensive the damage is.
Is there a way to determine if creep damage is a result of over temperature operation or over pressure operation as opposed to weld issues?
Oh, that's a good question. And I mean, in a lot of cases, again, when you do if you find damage, and if you do take a sample out and have the opportunity to look at the microstructure, then in most cases, in those cases, when you're able to look at the microstructure, you normally can distinguish between discontinuities in the structure that are related to an original weld defect and creep damage that's occurred in response to service-related loads. Where it can get to be a little bit complicated is if you have an original defect in the material and that has served as a preferred site for propagation of service-related damage, then the issue becomes, is that damage just isolated to that local area of the defect, or is the presence of the defect just highlighting the fact that the component as a whole is in distress? And that's again, that's where having the samples can be very important in accurately defining the extent of the damage.
Right. Okay, this question is what is a reasonable inspection frequency for high energy piping welds? Or can you answer that?
Well, I mean, obviously it depends on a lot of things. If you have a piping system that, first of all, has no long seam welds in it, which I don't think many of the combined cycle plants, as I said, long seam welds are usually not much of an issue there. But if you have a piping system that has been properly maintained, that you know that the supports are operating properly, you check the supports out on a regular basis, and assuming the piping system was designed properly, you're probably, inspection intervals for 50,000 hours are probably reasonable. But if there have been issues with the support of the system, or if there have been issues with the operation of the plant, it's operated above design temperatures for any of those reasons, then those have got to be evaluated on a case-by-case basis, and then modification of the inspection interval or reduction of the inspection interval that's consistent with the potential for distress, that modification needs to be made.
Okay. Scott, can we unmute Charles Turner, please? He's got a fairly long question. I think this will have to be our last one, but I'd rather he ask it than me to read through it all. We can do that. Charles, are you with us?
Yes. Hello. Yeah, we've recently issued NDE specs, with all this good information that's out there and within the user groups and such as this forum also. So we issue NDE specifications that reference the requirements to linear phase array and focus shear wave for the detection of the microcracking in long-term P91 operating systems. The specs were issued to major firms, major NDE firms, with responses coming back. They're not familiar with the requirements for the detection of the macro cracking, and they requested test blocks from us to allow them to set up for the process. Well, we don't have those. And is there an NDE standard that's being generated that could be referenced by this industry to utilize in the high energy piping NDE survey inspection program?
That's a great question, and first of all, I'm astonished that there are NDE providers out there that aren't familiar with the protocols. But
us too. That's what took us by surprise. And then the client comes back and says, "Okay, you spec'd it. Provide the blocks."
Yeah, I think this goes back to, again, about how much our industry has changed and how, in many ways, how weak we've gotten. But in answer to your question, I think the best resource for you is EPRI has set up a qualification program for NDE people, for NDE technicians looking to identify creep damage in high energy components, and I think that has been a very effective program. And I would direct you toward that. I mean, I know there are a number of operators out there who require that any NDE technicians who come in to do inspections on their piping systems, they require that they've gone through the EPRI program and be certified through that.
Yes, and that was carried in our specification for the EPRI certification, and I was just astonished at the lack of knowledge that was responded. And we're talking major, NDE firms.
Yeah, I agree with you. I mean, it's not only astonishing, it's really troubling.